Okay, well, let's get started. This is Jason Bloomberg with Intellyx. Our webinar is on avoiding the perils and pitfalls of cloud-based integration. I will be joined by Atul Saini, CEO of Fiorano Software, and our talk on avoiding the perils and pitfalls of cloud-based integration. There's my email address and my Twitter handle, the eBizWizard. Just a bit about me. I am president of Intellyx, an industry analyst firm focused on agile digital transformation. I also write 5 articles a month for Forbes, as well as several contributed blogs and my biweekly newsletter, The Cortex. My latest book, The Agile Architecture Revolution, is also still available, so definitely go ahead and look that up. Okay, so let's get started. So let's go back to the SOA days, service-oriented architecture days, the middle of the 2000s, around 2005, this is essentially a picture of the middleware story as of that period of time, right? SOA had just hit the scene, everybody was talking about it, and all the big vendors, middleware vendors, decided to come up with their own enterprise service buses. So they took their existing middleware, whatever it happened to be, broker, integration brokers, integration hubs, enterprise application integration tools, put web services on them, called them ESBs, and then connected them to any number of different endpoints, both back office endpoints, legacy endpoints, as well as front office, front customer-facing endpoints. But essentially, this was a centralized view of the world, right? This is 2005. It's really before the cloud hit the scene. So this was within the enterprise IT organization. It was managed centrally by the IT organization, and it connected to things within the enterprise. Now, business-to-business integration was a part of this story, but that was at this point in time difficult to do and typically relied upon other middleware in addition to the ESB. So the ESB story was really a centralized, internal to the enterprise infrastructure that supported the ability to connect any number of different clients. That could be web clients, they could be internal applications, to your various back-end systems and applications. Okay, well, along came the cloud. Cloud computing hit the scene around 2007, 2008, matured over the next few years, and of course now everybody is in the cloud. But we still have this challenge, right? How do we integrate applications in the cloud or between the cloud and our on-premise technology? Well, all the middleware vendors who spend all that time and money taking their old gear and putting web services interfaces on them back in the 2000s now are picking those things up and putting them in the cloud, right? So here's the question: is this the way to do it, right? Can you take your centralized enterprise middleware and just pick it up and run it in a virtual machine in the cloud, and is that the right way to do things, right? Well, the reality is this does not work very well, right? You don't take advantage of the benefits of the cloud this way, right? It's not particularly elastic. You don't deal with governance issues or automated recovery from failure issues. This is not really the right way to think about what it means to do integration middleware in the cloud. So you say, well, okay, this is sort of an overly simplistic diagram. What about this? What about basically taking this enterprise middleware and instantiating it for every customer, right? So what we have is a multi-tenant approach now to integration middleware in the cloud, but we're still not really doing it the way that will take advantage of cloud-based benefits. What we have here is we're taking existing software and putting it into a virtual machine instance for each customer, and you can get this to work, and a lot of vendors have gotten this to work, but you're not going to get the benefits of the cloud this way, where you're not going to get horizontal scalability, you're not going to get automated recovery from failure, you're not going to deal with data in a cloud-centric way, right? You're still connecting essentially to enterprise data sources in a traditional way. So even thinking about multi-tenancy at this level, where every virtual machine instance corresponds to a separate integration customer, is a step in the right direction compared to on-premise middleware, but we're still not taking advantage of the cloud to its full extent. The challenge that many enterprise middleware vendors, the big guys, are struggling with is that they really need to rethink what it means to do integration. right? Because this moving traditional middleware to the cloud isn't solving the problem. You're not getting the architectural benefits of the cloud. So what these incumbent middleware vendors, the big guys who shall remain nameless, what they have to do is they have to go back and rewrite their integration technology. Now, keep in mind, some of this gear has been around since the 1990s. When they moved to ESBs, they didn't start from a blank sheet of paper. They started from their existing middleware, added all the SOA stuff, web services stuff to it, but it's still old gear under the covers, right? It's designed to be a centralized broker of some sort, and as a result, there's an enormous investment necessary in order to completely rewrite software, middleware software, the infrastructure software, to really make it cloud-centric. Of course, this gives an opportunity for cloud-based vendors to come up with something that is new and better suited for the cloud. So there's this challenge, sort of, you're sort of stuck either between traditional, the big old guard incumbent vendors who are rewriting their software versus cloud players who may be still quite new in the market and trying to build capabilities. So what is it we're really looking for when we're thinking about cloud-based architectures? Well, first of all, we want to be decentralized. The digital story today is a decentralization story. We're no longer putting all our gear into our enterprise data center. We're leveraging not just one cloud environment, but potentially multiple cloud environments, and we're leveraging third-party assets to increasing extent. So if you look at your typical enterprise customer, yes, they might have their own on-premise gear, they might have some public cloud, they might have some private cloud, and then they might have Salesforce or other cloud-based services that they're integrating with that are essentially third-party cloud-based services. And that is the typical situation, right? We have many different cloud-based and on-premise-based technologies. So we still have to deal with performance, we still have to deal with security and governance across that decentralized, diversified, borderless enterprise. Of course, we want horizontal scale, right? We want unlimited horizontal scale. That's one of the reasons we moved to the cloud in the first place. And we want the cloud to essentially to handle that for us automatically, right? We want to have automated elasticity where we can scale up to deal with spikes in demand, scale back down to save money. And we don't want to have to spend a lot of time monkeying with that, right? We want the cloud to take care of that for us. So it should happen behind the scenes, right? So if we're focusing on, business functionality, we shouldn't have to worry about what do we need to do to code for elasticity, right? We want that to be part of our cloud-based infrastructure. Multi-tenancy is a key part of the cloud value proposition, not just that brute force multi-tenancy from a couple of slides ago where we pick up old gear and stick it in a virtual machine instance, where we want to be more sophisticated about how we deal with multi-tenancy. We may have certain capabilities that are shared across different companies, or other capabilities are unique to individual companies. We want to make sure that we are able to provide the adequate security so various instances are separate from each other, but we still want to share underlying infrastructure in a way that is cost-effective and highly performant. So multi-tenancy is not just a black and white thing. It's not is or isn't it multi-tenant, but there are various types of multi-tenancy, and the challenge here is to get the best combination of capabilities. So you want the best security, but you also want the best bang for the buck, right? The most efficient, cost-effective way of building a scalable infrastructure, especially when you're looking at these cloud-based integration vendors who have many different customers. So what they're doing is they're passing along the cost, the efficiencies, the scale efficiencies to all of their customers, and they have to get this right, so that the customers are getting the cost effectiveness as well as the security they require. And then automated recovery from failure as well is a different way of looking at dealing with quality and performance issues in the production environment that the cloud has really reinforced for all enterprises. Whether or not you're actually talking about a particular system being in the cloud or not, automated recovery from failure is essentially now a central architectural best practice. Back in the old days, we were trying to avoid failure, right? There was all about, 5 nines of reliability. If we were at 4 nines, we'd pay extra money to get to 5 nines. The whole idea with that levels of reliability is to reduce failures, right? Try to get them to as close to 0 as we can. And as we got past the 5 nines, a few hours of downtime a year, try to shrink that down, it became very, very expensive because it's very difficult to prevent all failures in a complex enterprise environment. A much more cost-effective way as well as scalable way is to plan ahead for failure. This is the way the cloud is built, right? Instances go down all the time, and you don't want to be in a situation where an overall application fails because an instance here or there has some sort of issue. If an instance fails or has a problem, deprovision it and reprovision a replacement, and do that automatically, and automatically replace instances or whatever it is that goes down. You want to automatically replace them. So this is a fundamental part of how we build gear for the cloud, and really how we want to think about building gear for enterprise technology overall. So when it comes to integration middleware, we want to make sure that every element of that integration middleware has automated recovery from failure. So any piece of the story might fail. Right, it could be sort of the underlying message flows, they might fail. It could be the endpoints might fail. The endpoints that are remote connecting you to Salesforce might fail. The endpoints that are in on-premise connecting to your legacy systems of record. Anything could fail. So the challenge here is, from an architectural perspective, plan ahead so that you have an automated way of recovering from failure, so that while you're going through that automated recovery process, the performance of the overall application ideally isn't impacted, right? You have a sufficient redundancy and sufficient ways of routing around problems. So even if this instance or that instance goes down and has to be bootstrapped, it might take you half an hour or whatever, hopefully not half an hour, but you never know, that you have enough other instances that can take over the traffic. So if you think about what it takes to build integration technology, what does it take to build middleware? Building middleware with automated recovery from failure requires a level of architectural expertise and maturity that you just didn't see from the middleware gear 2005 and before. It was just not part of the mentality, and that's really a key part of the story here, is what does it take for a middleware vendor to architecturally design their gear with automated recovery from failure as part of the principles of that technology. Another key capability that the cloud has emphasized for us is that we want to have asynchronous behavior as our default message pattern. Right, instead of synchronous behavior being the default, which is what we're used to from the 1990s, from the original Web 1.0, was a synchronous model, right? Click a button, wait for a response, and that's just the way we expected things to behave. And that happened behind the scenes as well, where the way middleware interacted, it was a request-response model. Well, today in the cloud, asynchronous behavior should be the default. We don't want blocking. We don't want to wait around for a response, and we want to deal with state information and other elements of the asynchronous pattern in a way that enables us to get this level of scale and the automated recovery from failure that we desire. So we need to distribute our processing in parallel, without having to worry about when one process stops for another one to start. And there's a number of different asynchronous patterns that follow this. So queuing has been around for many years as 1990s technology. That's asynchronous pattern. Publish subscribe is an asynchronous pattern. And then we're used to asynchronous pattern on the user interface as well. I call this the Facebook effect. Right? Before Facebook came along, asynchronous behavior on the user interface, we had AJAX and we saw it here and there. But now if you think about how Facebook works, it just established asynchronous pattern for everybody to see. And now everybody expects a screen to just update itself, right? You don't have to click refresh to get the Facebook screen to update. And now we're expecting that from all of our technology, and that's essentially the asynchronous pattern now becoming the default pattern for message interactions across the board, not just the user interface, but throughout the story. So here we have the challenges now for middleware: asynchronous behavior by default, automated recovery from failure, and horizontal scalability. And those are the challenges that any integration in the cloud, integration as a service or cloud-based middleware, however you want to look at it, should be able to meet that requirement. So iPaaS, that's integration platform as a service. Here's some basic capabilities you would expect from any iPaaS service. Well, there should be a configuration environment, right? If it's platform as a service, the idea there is there are interfaces not just for the end user, but for developers, for integration people, and it should be a configuration-based user interface for setting everything up. So that's part of the platform aspect of platform as a service. We want to abstract the cloud capabilities, right? We don't want to have to code hands-on our recovery from failure. We don't want to have to code our elasticity. We want the platform to take care of that for us, right? So we're abstracting all that out. It's there. We can rely upon it, all the security, all the scalability, but we don't want to have to monkey with it unless we have some sort of specialized situation. We want to be able to integrate arbitrary endpoints, right? This is one of the things that REST has brought to the table, right? REST lets us integrate with most endpoints that are out there, but even if we have other kinds of endpoints, we want to be able to integrate with them. So we need the appropriate connectors or other technology so that it doesn't matter what endpoints we have, we want to be able to connect anything to anything. And then, of course, we want security and governance, but security and governance can't be handled the old, slow, paperwork-laden, ask IT to do something for you kind of approach. It should be policy-driven. That is, we should be able to go in and configure the policies to drive our security and governance, and that gives us the ability to automate how we deal with security and governance. And that's how we keep those important enterprise issues from becoming bottlenecks or remaining bottlenecks. We don't want them to be bottlenecks anymore. So what I've essentially done here is sort of laid the groundwork. What does it mean for an enterprise middleware vendor to be truly cloud ready? And that's essentially the setup now for the discussion that Atul will take over. So that's it for my slides. Here's my email address again and my Twitter handle. And if you can't wait to get the slides from Fiorano, you can send an email to this email address. It's an autoresponder, perils@Intellyx.com. Send it right now on your phone. You all have your phones in your pocket, I know. And you can send that right now. You'll get back one and only one email with a link to the deck on SlideShare and a little bit other information from Intellyx. And that's it for my talk. So I will hand over the presentation to Atul, and hopefully he is ready. And here we are. Okay, Atul, take it over.
Okay, here we are. Okay. Hi, everybody. I'm Atul Saini. I'm the founder of Fiorano Software. We have been actually building and deploying a peer-to-peer distributed integration platform for many years now, and it has a lot of the behaviors that Jason talked about. So what we're going to be talking about is the cloud integration challenges, performance and scalability. Just to summarize, elasticity, failure recovery, management and security. As Jason had mentioned, legacy integration technology really isn't designed to handle a lot of these challenges in the cloud environment. It works very well in a single enterprise environment, but it's not designed for the cloud environment. So let's talk about what we can do to get a system in place that works very well in the cloud. One of the key things about the cloud is horizontal scalability. So what you see on the screen here is, a classical hub and spoke integration server. And we've separated that out into two sort of parts where you have a management and repository functionality and the processing functionality, the integration processing functionality. In a typical hub and spoke architecture, these are all melded into one big hub where you have a lot of the services, the adapters, the tools connecting, you compose your flows there, and then you deploy them into the hub, and they all execute at the hub. So the problem with that is that it can't take advantage of the horizontal scalability of the cloud. So the way you actually go about solving that issue and creating something that takes advantage of the horizontal scalability of the cloud is by separating out the processing functionality from the management functionality. So for instance, you have two applications, A and B, talking to each other through a hub, but if you have extra load coming on, let's say a third application, let's say there are 50 applications and app on server 1, right? App 1 to app 50. And the additional application that comes along is slowing down the hub. So if you have a cloud environment, you want to logically, in the same flow, deploy additional services to integrate, but they can't be running on the same hub. So you can deploy an additional peer server to take advantage of the horizontal scalability of the cloud. And this process scales. For instance, what you can have is you could have 4 processing peers and multiple applications. Here you have 3 applications in the upper part of the top 2 peer servers integrating 3 applications, apps 1, 2, and 3, and the bottom 2 servers are integrating apps 4 and 5. We use the term apps here, but really what you're going to be integrating are the microservices or the services that are connected to the applications. So this kind of system scales linearly. That means that it takes advantage of the horizontal scalability of the cloud. As your load increases, you don't kill a single hub, or you don't actually have to. One of the arguments that can be made by hub and spoke vendors is that you can just replicate the hub, but that doesn't really work very well. What you really have to do is, because it's not really designed to allow additional services to be deployed on different parts of the cloud very easily. So unless it's designed that way up front, you can't just replicate a hub. In typical architectures, the legacy architectures, when you create an integration flow, the entire flow has to run on a single hub. It can't run across multiple hubs. And to make that happen, you have to do a tremendous amount of surgery. In this particular set of flows, what you're seeing here is linear scalability. So this takes advantage of all of the parallel processing that is inherent in the flow. For instance, apps 1, 2, and 3 don't share any data with apps 4 and 5. That means that the two flows can run in, two subflows can run in parallel, although they may logically be part of the single large integration process that the end user is trying to deploy. So this way, the peer-to-peer architecture that we're talking about, that we've actually implemented, takes advantage of all of the parallelism that is already inherent in the flow. So data can be exchanged. And another point is that because the system is completely asynchronous, new applications can be deployed at runtime, and all of the services and applications are stored in the management and repository server. So at runtime, what one can do very easily is, without stopping the existing system, new flows, new services can be taken from the management and repository server and deployed onto any peer server. The important point to note over here is that you don't actually have to stop an existing application to extend its functionality. This has a lot to do with the asynchronous operation as well. So what I'm doing here is presenting the peer-to-peer part of the presentation first, and then talking about asynchronicity, but the two are very melded together. The application model in this sort of system, which actually maps very well to the cloud, is that multiple services simply send messages to each other. The messages are transferred via message queues. So what you're seeing here in the dark blue lines are message queues from service 1 going to service 3 over in a peer-to-peer manner, and app 4 to app 5, etc., etc. In apps 1 and 2, they're communicating via just a single peer server. So in that case, that peer server is a hub. There are many benefits to this kind of architecture from a failure recovery standpoint as well. For instance, if the first peer server goes down, applications 1 and 2, you can set up a configuration so that one of the other peers serves as a backup for any particular peer server in the cloud, and that's something that is quite common in a peer-to-peer architecture of this kind. The management and repository server, you only need a single management and repository server that is in a central location. So control is centralized while data flow is distributed and parallel. So this gives you linear scalability, taking advantage of the horizontal scalability of the cloud, while giving you the control benefits of a hub and spoke architecture from a management and security standpoint. Now, the same architecture also works across multiple clouds. What we showed you, what you were seeing was all in a single cloud. You could see multiple peers in a single cloud. But as far as the system itself is concerned, it doesn't really matter where the peer servers are. So you could have one set of peer servers in a cloud in New York, and you could have another set of peer servers in a cloud in London, and it could all be controlled with a management and repository server in Chicago. So The architecture is location independent. Any of the components in the architecture, the peer servers or the management and repository server, those are the big infrastructure components, right? And this level of flexibility is essentially possible because of the asynchronous nature of the communication, and we'll talk about that in a minute. Now, in terms of another benefit of the elasticity is here you've got a cloud. We're going to illustrate the concept of dynamically determining slow components. Suppose you have an integration flow and you deploy a particular service on a messaging peer and you find, well, it's very slow. It's not running fast enough. Well, what you can do in this kind of architecture with the asynchronous model is that you can take the particular service that was slow and dynamically, without stopping the system, deploy it on one of the faster peers. You know which of the peer servers that are fast and which are slow because you got this information in the management and repository server. The management and repository server is only getting control signals. The most important point is data always flows through the peer servers, while you only need a single management and repository server because only control information goes to the management and repository server. So once again, you have a situation where one of the servers is overloaded, one of the processing peer servers is overloaded, and then you can determine that and dynamically deploy the additional component or a set of components at runtime on one of the unloaded peers. So this sort of takes advantage. It can be thought of as a failure. Failure recovery, automated failure recovery works in exactly the same way. It's essentially like taking components from one particular peer server and running them on a different peer server. If the entire peer server goes down, you could use a similar technique, and that's what we've implemented, to actually move the peer servers over. So this way you can actually identify bottlenecks. This is a huge issue in integration today. With all current technology, with all legacy servers implemented by any of the tier 1 vendors, you essentially have a process-centric flow model. And if you have a flow model, let's say BPEL style, right? It's not exactly BPEL, everyone has a variant of some kind. But if you have a component in the middle that's slow, there's nothing you can do except buy more processors and then pay a lot more money and try to speed everything up. You can't take that one particular component at one time and move it off to a faster machine because the flow model is not asynchronous and it doesn't support that. Now, if you want to implement an asynchronous flow model on top of a synchronous system, you have to do a lot of programming, and essentially like rewriting everything from scratch. That's really what it boils down to. So now in this sort of asynchronous distributed peer-to-peer architecture, it's a handful, but it's not very complex because in the worst case, the peer-to-peer architecture becomes, with a single peer, becomes like a hub and spoke system. But the asynchronous model is a big differentiating feature of a functional system. So here what you have is integration flows are created in software tools like a Studio, which is connected to the management and repository server. So here you have an integration flow. Conceptually, you have a service A sending a message to X, sending a message to B and C, and then goes to Y, D, and C. These are directional. Now, what happens at runtime is, unlike there is no central process model, process engine, anything like that. A, X, B, C, Y, D, Z, all of these are simple services. Like you could think of them as messaging applications using the JMS API. At runtime, what will happen is that basically all of these services are deployed dynamically to a particular peer server. So for example, A and X are running in the peer server in location A, B and C are running in location B peer server, and location C's peer runs D, Y, and Z. So what happens is basically these are dynamically deployed at runtime onto the peer servers. Dynamic deployment means you actually copy the jar files of the particular service onto the particular peer server, and then the whole process starts running. There's just a trigger, and message flows start executing. A sends a message to X. How does X send a message to both B and C? Well, the graph that that's on the management repository server has embedded in it the information that hey, when X produces an output, it's got to go to B and C, and that information is sent to both the messaging peers. So when X produces a message, the messaging peer in location A has the encoding to say, well, I need to send this to location B, and when that peer server receives the message, it knows it's got to give it to both B and C, or to whichever component is there. So this is how the flow model works, and this asynchronous flow model obviously is very, very scalable. So the asynchronous means that basically there's no blocking call in the system at all. So from the standpoint of functionality, all of these components, A, X, B, C, D, Y, Z, they're running in their own processes, and they're actually quite oblivious. They're actually quite oblivious to the fact that A's output is going to X, or X's output is going to B and C. They actually don't even know that, and they don't need to, because the whole system is asynchronous. Now, you can always build a synchronous connection on top of an asynchronous core, but not the other way around. And this is the principal reason why integration is expensive today, is that all of the integration and most of the integration engines in the market today are built on a synchronous core, and which is very inefficient, right? In our case, the peer servers are all based on a messaging core, and so the entire system is asynchronous, and you can build a blocking call on top of that architecture. So what is asynchronous messaging? Here's a simple set of illustrations. You've got three services, A, B, C1, and C2. When they're run, let's say A sends a message to B and B sends a message to both C1 and C2. So what happens at runtime is that A's message is actually going to a message queue, which is then sending it to B. Now the benefit of this system is that what if application service B is running very slowly? A keeps producing messages at 1,000 messages per second, to take an extreme example. B is processing at 10 messages per second, so there's 990 messages a second that are being buffered up in the queue, right? So asynchronous messaging allows any particular service to run at its own speed. This is not possible in a synchronous system. In a synchronous system, message would go to A would produce the output really fast, it would go to B, everything would wait, and then that message would go to C1 and C2, wait for a reply, and it'll all go back to A, saying, all right, it's processed, and then A would process the second message. So A would, in a synchronous system, you slow down to the speed of the slowest service. In an asynchronous system, you don't slow down. You go as fast as you want. Now, what happens if B is really slow? Well, what you can do is, because we've got a peer-to-peer architecture taking advantage of the horizontal scalability of the cloud, you can start another instance of B in any other machine in the cloud, as long as that's got a peer server. So this is something that you can do immediately. You can do this today. You can decide a fan out. If you have, for example, an expensive operation like a transformation, you could set up 20 peer servers and perform 20 transformations in parallel and get the results back. A lot of applications require certain ordering in the results, and you can give it to an ordering sequencer and get the answer. So this is a very common pattern. So obviously, in a peer-to-peer infrastructure, you've seen from the diagrams that there's no single point of failure. You can have multiple peers, and you can set one peer to back up another peer, right? So each peer can have its own set of backups. It's difficult to imagine a situation where all of them die at the same time. But the peer-to-peer model automatically incorporates HA. Of course, the implementation is not particularly easy, but because of the fact that the application model is asynchronous, if there's a failure in one of the peers, there's really no problem. What happens is that messages keep getting buffered in the queue. There is no central database in this system. And we'll talk about that in a second. One of the other things that you can do with an asynchronous system is you can temporarily suspend part of the flow and examine the contents of messages, which helps a lot in the process of deployment. So for instance, suppose you have following integration flow, right? 1 to 3 to 4 to 5, whatever. Now, with message interception, one of the things you can do is you can decide to intercept the message, and at this point, messages produced by component 2 will simply keep getting backed up on the cloud. And once you've decided to examine the messages and maybe even change them for debugging purposes or whatever you want, at runtime, you get calls. In a live running system, you can actually put message interceptors and examine data. These are kinds of things that are not particularly easy to do in traditional technology, right? And you can then continue the flow. The asynchronous model, it's not just the peer-to-peer architecture that simplifies failure recovery. You see, the two go hand in hand. You need a distributed peer-to-peer architecture to take advantage of the horizontal scalability of the cloud, but it needs to be combined with a fully asynchronous application model. Asynchronous application models mean that the application is essentially like it's like a message queuing application. That means that if you have 20 different message queuing clients, they're sending messages to each other, but when one sends a message, it doesn't really know who's getting it. The target of the message is determined externally by the topic of the queue on which the message is published, right? Now, the benefit of this architecture is if any of the peer servers, any of the infrastructure goes down, it's not a problem because the state of the flow is just the set of messages, and the messages are guaranteed delivery. So suppose all the peer servers go down, it's not a problem. The messages are in the queues. When they come up again, you still got the whole system, right? Now, this is again very different because the queues are distributed across the cloud, right? The speed is a lot. The performance is very good because it's distributed parallel. If you have a single centralized database, which is what you have in a classical hub-and-spoke architecture, with a synchronous model, you have to keep updating that database all the time, really, really fast. That's a process called hydration. That's not something that sales guys tell you when they're selling you the software, but you should try it, right? So the performance becomes a massive bottleneck, and you need to buy, extremely expensive storage systems to take advantage of that. That whole problem disappears entirely with an asynchronous architecture, which is why really a lot of the tier one vendors are now looking to rewrite the software. So in an asynchronous system, you pick up where you left off when the system resumes. So time's almost up, so we'll just talk a little bit about management and security. There's a policy-driven distributed security model. So there's a central configuration for all security. The security descriptors are then distributed to each peer server, and everything is managed in a distributed manner, so performance is not an issue. And scales out into multiple clouds. For each cloud, you can set separate policies. It's something that we would probably need a separate webinar for. But I think at that point, I'm done. We can open it up for questions. Okay, this is Atul. So the first question is, can you build a sync service if required? And what about sequential message requirements in which you could proceed that wouldn't suit the cloud auto spin up of new queue? Good question. You can always build synchronous services on top of an asynchronous architecture because you add a synchronizer. Synchronizer means you send a message and you add the JMS API has a provision for this. You can always send a message, it goes asynchronously and it comes back. But as far as the user is concerned, the interface is synchronous. So building a sync service is not a problem. We do it all the time. Sequencing, yes, sequencing is an issue. Sequencing is something that always slows you down. You can produce a lot of results in parallel, and that's something you have to manage as a developer. So your service design has to measure that. Suppose you have a service with 5 instances of that, and you're producing the results. You will have to add some sequencing information to the actual data that is in each result, and then resequence everything. That's how it would work. Second question, can you explain something about your asynchronous application model and the ACID transaction concept? That's always something that comes up. The ACID transactions are typically done best there is a limitation as far as ACID transactions go from the standpoint of the fact that ACID transactions can't be distributed asynchronously. So if you want to do an ACID transaction, you really have to take a single component and act as if that transaction is happening in that component. You can fan data out to different components, but that component will have to act as the synchronizer for the transaction. Absolutely. So yeah, ACID transactions is, in most integration, integration itself is different from interaction. That's a very important point to understand. Integration really means pull data out of an application, transform it, and send it to some other app. It's inherently an asynchronous operation. Interaction is really what most people call it integration. That's that concept, right? What they're really talking about is interaction. Interaction is a classic synchronous request reply. Now, I got two things that need to be updated in the database: ACID transaction. So yes, if you, the fully distributed parallelized asynchronous model has a disadvantage there. How does the endpoint find its new target once you reposition it to a faster pair? Aha, that's a good question. Well, that's the secret sauce in the implementation, right? And the secret is that the graph of the flow is directional, and that information is available at all the pairs. So that's obviously anyone implementing such a system has to make sure that the proper targets are picked up. So it's really an implementation. It's an implementation detail. Another question that a reader has come up with is, in your peer-to-peer model of message hubs, can applications on mobile devices send messages to back-end applications the other way around? Yes, the application on the mobile device typically will communicate via a REST service of some kind, which can be hosted in an API management platform. The mobile device will have to use some sort of API. And the popular way to do that, I mean, there's no magic. The message has to somehow come to a peer server of some kind, right? So one will have to create a microservice or an adapter or a component. You can call these a service of some kind, which is receiving the message from the mobile application. You don't have a peer server on every mobile system, on every phone. That's not the case. You would use something like API management to have a REST API, which is the API that is used to create the particular mobile application, and that's how you would then communicate with the peer server. Is a trial version available for your product? Yes, it is. It's on the website, fiorano.com. You can certainly get a trial version from there. I think that covers all the questions. There was just a bit of a mix-up. Tom was supposed to make a presentation on the questions, but I've just gone ahead and done so myself. Can Fiorano interface with other middleware tools such as web methods? Yes, it can. And the way that happens is just via an adapter. All the components that connect to peer servers are services or microservices. You can build a service that talks to TIBCO, that talks to IBM, to Oracle. We've built such services, and typically large organizations have bought every kind of middleware in the search to reduce the cost of their integration. But the biggest cost in integration is not the infrastructure, but the services, the actual time and materials work that goes around it. One of the biggest benefits of the asynchronous flow model is that you can really literally get the job done with half the programmers in half the time. Now, lots of people don't like this because it's a sensitive issue. If I can sort of reduce the time by 80% and reduce the resources, and instead of 4 people taking 4 months to do it, 2 people can take 2.5 months to do it. It's theoretically very good for the company, but it's not always the best thing for the team. So it can get to be a very political issue. And so that's something to bear in mind. And it's an extremely sensitive issue, especially in government organizations, especially in today's economy, with things happening around the world. I think that was the last question. So unless someone has another question or wants to type another question, please feel free to get a copy of the product on the website. And we will go from there. Feel free to send email to me personally, atul@fiorano.com, or Jason, and we'll be very happy to respond. All right, everybody, thank you very much. We shall have a copy of this webinar on our website within the next day, and you can get a copy of the entire deck whenever you wish. Thank you very much.